Network Working Group request for comments 1950 category informational by P. Deutsch, Deutsch. I could be butchering that. Aladdin Enterprises J-L dot GAILLY info-zip May 1996. ZLIB compressed data format specification 3.3 status of this memo. This memo provides information for the internet community. This memo does not specify an internet standard of any kind. Distribution of this memo is unlimited. IESG note: the IESG takes no position on the validity of any intellectual property rights statements contained in this document. Notices: copyright 1996, L. Peter Deutsch and Jean Loup Gailey. Permission is granted to copy and distribute this document for any purpose and without charge, including translations into other languages and incorporation into compilations, provided that the copyright notice and this notice are preserved and that any substantive changes or deletions from the original are clearly marked. A pointer to the latest version of this and related documentation in HTML format can be found at the URL ftp://ftp.uu.net/graphics/png/documents/zlib/zdoc-index.html. Abstract. This specification defines a lossless compressed data format. The data can be produced or consumed even for arbitrarily long sequentially presented input data stream using only a priori bounded amount of intermediate storage. The format presently uses the deflate compression method but can easily extend to use other compression methods. It can be implemented readily in a manner not covered by patents. This specification also defines the Adler32 checksum, an extension and improvement of the Fletcher checksum, used for detection of data corruption, and provides an algorithm for computing it. Okay, end of page 1 of RFC 1950. Table of contents. 1. Introduction. 1.1. Purpose. 1.2. Intended audience. 1.3. Scope. 1.4. Compliance. 1.5. Definitions of terms and conventions used. 1.6. Changes from previous versions. 2. Detailed specification. 2.1. Overall conventions. 2.2. Data format. 2.3. Compliance. 3. References. 4. Source code. Going to scroll down to make some more room here. 5. Security considerations. 6. Acknowledgements. 7. Authors' addresses. 8. Appendix rationale. 9. Appendix sample code. 1. Introduction. 1.1 Purpose. The purpose of this specification is to define a lossless compressed data format that bullet point is independent of CPU type, operating system, file system, and character set, and hence can be used for interchange. Bullet point can be produced or consumed even for an arbitrarily long, sequentially presented input data stream using only a priori bounded amount of intermediate storage, and hence can be used in data communications or similar structures such as Unix filters. Bullet point can use a number of different compression methods. Bullet point can be implemented readily in a manner not covered by patents and hence can be practiced freely. The data format defined by this specification does not attempt to allow random access to compressed data. So end of page 2. On to page 3 of RFC 1950. 1.2 Intended audience. This specification is intended for use by implementers of software to compress data into ZLIB format and/or decompress data from ZLIB format. The text of this specification assumes a basic background in programming at the level of bits and other primitive data representations. 1.3 Scope. The specification specifies a compressed data format that can be used for in-memory compression of a sequence of arbitrary bytes. 1.4 Compliance. Unless otherwise indicated below, a compliant decompressor must be able to accept and decompress any data set that conforms to all the specifications presented here. A compliant compressor must produce datasets that conform to all the specifications presented here. 1.5 Definitions of terms and conventions used. Byte, 8 bits, stored or transmitted as a unit, same as an octet. For this specification, a byte is exactly 8 bits, even on machines which store characters on a number of bits different from 8. See below for the numbering of bits within a byte. 1.6 Changes from previous versions. Version 3.1 was the first public release of this specification. In version 3.2, some terminology was changed, and the Adler32 sample code was rewritten for clarity. In version 3.3, the support for a preset dictionary was introduced, and the specification was converted to RFC style. 2. Detailed specification. 2.1 Overall conventions. In the diagram below, a box like this, the vertical bars might be missing. And we just... Okay, so a box like this, vertical bars might be missing, represents 1 byte, and a box like this, so with equal symbols instead of dashes, represents a variable number of bytes. Bytes stored with a computer do not have a bit order, since they are always treated as a unit. However, a byte, considered as an integer between 0 to 255, does have a most and least significant bit, and since we write numbers with the most significant digit on the left, we also write bytes with the most significant bit on the left. In the diagrams below, we number the bits of a byte so that bit 0 is the least significant bit, i.e. the bits are numbered 0, 1, 2, 3, 4, 5, 6, 7. Within a computer, a number may occupy multiple bytes. All multi-byte numbers in the format described here are stored with the most significant byte first at the lower memory address. For example, the decimal number 520 is stored as. So we got 0 and 1, the more significant byte, 2 multiplied by 256, and the less significant byte. So is that network byte order or not? Less significant byte and more significant byte. I believe that is big endian, because big endian is an order where you don't have to mentally remap the number in your head, because the order of the bytes in an array match the order of the bytes in a number. 2.2 data format. A ZLIB stream has the following structure. So we have a 0 and a 1 box, CMF, FLG, and then more. We're on to page 5 of RFC 1950. If FLG.FDICT set, and 0, 1, 2, and 3 on a, I guess these are the bits of a half octet. Dict ID, more, and then we have some bytes of compressed data. Then we have Adler 32 bits, maybe 4 bits possibly. Any data which may appear after Adler 32 are not part of the ZLIB stream. Okay. CMF, compression method and flags. This byte is divided into a 4-bit compression method and a 4-bit information field, depending on the compression method. Bits 0 to 3, CM, compression method. Bits 4 to 7, CInfo, compression info. CM, compression method. This identifies the compression method used in the file. CM equals 8 denotes the deflate compression method with a window size up to 32K. This is the method used by gzip and PNG. See references 1 and 2 in chapters 3 below for the reference documents. CM equals 15 is reserved. It might be used in a future version of the specification to indicate the presence of an extra field before the compressed data. Alright. CInfo, compression info. For CM equals 8, CInfo is the base 2 logarithm of the LZ77 window size minus 8. CInfo equals 7 indicates a 32K window size. Values of CInfo above 7 are not allowed in this version of the specification. CInfo is not defined in the specification for CM not equal to 8. Then we have FLG, flags. FL is capital, A is lowercase, G is uppercase, and S is lowercase, so it's just like describing how to understand the abbreviation. This flag byte is divided as follows. So we have bits 0 to 4, fcheck, check bits for CMF and FLG, bit 5, fdict, preset dictionary, bits 6 to 7, flevel, compression level. The fcheck value must be such that CMF and FLG, when viewed as a 16-bit unsigned integer stored in MSB order, and then within parentheses, CMF multiplied by 256 plus FLG is a multiple of 31. Multiple of 31. That's okay. Not 32, but 31. Okay. End of page 5, on to page 6 of RFC 1950. FDICT preset dictionary. FDICT preset dictionary. If FDICT is set, a DICT dictionary identifier is present immediately after the FLG byte. The dictionary is a sequence of bytes which are initially fed to the compressor without producing any compressed output. DICT is the Adler32 checksum of this sequence of bytes. See the definition of Adler32 below. The decompressor can use this identifier to determine which dictionary has been used by the compressor. F level, compression level. These flags are available for use by specific compression methods. The deflate method, CM equals 8, sets these flags as follows. 0, compressor used fastest algorithm. 1, compressor used fast algorithm. 2, compressor used default algorithm. 3, compressor used maximum compression slowest algorithm. The information in F level is not needed for decompression. It is there to indicate if recompression might be worthwhile. Compressed data. For compression method 8, the compressed data is stored in the deflate compressed data format as described in the document deflate compressed data format specification by L. Peter Deutsch. See reference 3 and chapter 3 below. Other compressed data formats are not specified in this version of the ZLIB specification. Adler32 checksum. This contains a checksum value of the uncompressed data, excluding any dictionary data, computed according to Adler32 algorithm. The algorithm is a 32-bit extension and improvement of the Fletcher algorithm, used in the ITU-T space x.224/ISO 8073 standard. See references 4 and 5 in chapter 3 below. Adler32 is composed of two sums accumulated per byte. S1 is the sum of all bytes, S2 is the sum of all S1 values. Both sums are done modulo 65521. S1 is initialized to 1, S2 to 0. The Adler32 checksum is stored as S2 multiplied by 65536 plus S1 in most significant byte first network order. Page 7, RFC 1950, 2.3 Compliance. A compliant compressor must produce streams with correct CMF, FLG, and Adler32, but need not support preset dictionaries. When the ZLIB data format is used as part of another standard data format, the compressor may use only preset dictionaries that are specified by this other data format. If this other format does not use the preset dictionary feature, the compressor must not set the FDICT flag. A compliant decompressor must check CMF, FLG, and Adler32 and provide an error indication if any of these have incorrect values. A compliant decompressor must give an error indication if CM is not one of the values defined in the specification. Only the value 8 is permitted in this version. Since another value could indicate the presence of new features that would cause subsequent data to be interpreted incorrectly. A compliant decompressor must give an error indication if FDICT is set and DICT ID is not the identifier of a known preset dictionary. A decompressor may ignore F level and still be compliant when the ZLIB data format is being used as part of another standard format. A compliant decompressor must support all the preset dictionaries specified by the other format. When the other format does not use the preset dictionary feature, a compliant decompressor must reject any stream in which the FDICT flag is set. References. And this is section 3. 1. Deutsch LP gzip compressed data format specification available in ftp://ftp.uu.net/pub/archiving/zip/doc. 2. Thomas Beutel PNG portable networks graphics specification available in ftp://ftp.uu.net/graphics/png/documents. 3. Deutsch LP deflate compressed data format specification available in ftp uu.net/pub/archiving/zip/doc. 4. Fletcher, J.G., an arithmetic checksum for serial transmissions, IEEE, transactions on communications, volume com-30, number 1, January 1982, pp 247-252. 5. ITU-T, recommendation X.224, Annex D, checksum algorithms, November 1993, pp.144, 145, available from gopher://info.itu.ch, ITU-T X.244, also the same as ISO 8073. Page 8 of RFC 1950, source code number 4. Source code for a C language implementation of ZLIB compliant library is available at ftp://ftp.uu.net/pub/archiving/zip/zlib. 5. Security considerations. A decoder that fails to check the Adler32 checksum value may be subject to undetected data corruption. 6. Acknowledgements. Trademarks cited in this document are property of their respective owners. Jean-Luc Gailly and Mark Adler designed the ZLIB format and wrote the related software described in the specification. Glenn Randers-Fearson converted this document to RFC and HTML format. Then we have authors' addresses. L. Peter Deutsch, Aladdin Enterprises, 203 Santa Margarita Ave, Menlo Park, California, 94025. Phone 415-322-0103, AM only. Fax 415-322-1734. Email ghost@aladdin.com. Jean-Luc Gailly. Email gzip@prep.ai.mit.edu. Questions about the technical content of the specification can be sent to email. Questions about the technical content of the specification can be sent by email to Jean-Luc Gailly, gzip@prep.ai.mit.edu, and Mark Adler, madler@alumni.caltech.edu. Editorial comments on the specification be sent by email to L. Peter Deutsch, ghost@aladdin.com, and Glenn Randers-Fearson, randeg@alumni.rpi.edu. Page 9 of RFC 1950, Section 8, Appendix Rationale. 8.1 Preset Dictionaries. A preset dictionary is specifically useful to compress short input sequences. The compressor can take advantage of the dictionary context to encode the input in a more compact manner. The decompressor can be initialized with the appropriate context by virtually decompressing a compressed version of the dictionary without producing any output. However, for certain compression algorithms, such as the deflate algorithm, this operation can be achieved without actually performing any decompression. The compressor and decompressor must use exactly the same dictionary. The dictionary may be fixed or may be chosen among a certain number of predefined dictionaries according to the kind of input data. The decompressor can determine which dictionary has been chosen by the compressor by checking the dictionary identifier. This document does not specify the contents of predefined dictionaries, since the optional dictionaries are application-specific. Standard data formats using this feature of the ZLIB specification must precisely define the allowed dictionaries. 8.2, the Adler32 algorithm. The Adler32 algorithm is much faster than the CRC32 algorithm, yet still provides an extremely low probability of undetected errors. The module or unsigned long accumulators can be delayed for 5552 bytes, so the module operation time is negligible. If the bytes are A, B, C, the second sum is 3A plus 2B plus C plus 3, and so is position and order sensitive, unlike the first sum, which is just a checksum. That 65521 is prime is important to avoid a possible large class of 2-byte errors that leave the check unchanged. The Fletcher checksum uses 255, which is not prime, and which also makes the Fletcher check insensitive to single byte changes. And we have 0, and then I think that's like a not equal symbol. 0 not equal to 255. Yeah, I'm not sure what that's supposed to mean. The sum S1 is initialized to 1 instead of 0 to make the length of the sequence part of S2 so that the length does not have to be checked separately. Any sequence of zeros has a Fletcher checksum of 0. Okay, and then page 10 of RFC 1950. 9 appendix sample code. The following C code computes the Adler32 checksum of a data buffer. It is written for clarity, not for speed. The sample code in the ANSI C programming language. Non-C users may find it easier to read with these hints. And bitwise and a greater than is a bitwise right shift operator when applied to an unsigned quantity, as here. Right shift inserts 0 bits at the left, so it does a 0 fill extension. Then we have less than, bitwise left shift operator. Left shift inserts 0 bits at the right. Plus plus, and then within quotations, n plus plus increments the variable end. Percentage sign is a modulo operator. A%b is the remainder of a divided by b. Hashtag define base 65521. Comment largest prime smaller than 65536. Comment update a running Adler32 checksum with the bytes buff 0 to length -1 and return the updated checksum. The Adler32 checksum should be initialized to 1. Usage example. Unsigned long Adler equals 1 long, while read buffer, and we have the buffer and the length of the buffer, and if that read does not result in a end of file marker, Adler equals update Adler32, and it takes the Adler, buffer, and the length. If Adler not equal to original Adler, then there is an error. Okay. Unsigned, wait, that was a comment? Hold on. Okay, alright. So that was just a comment. Unsigned long update Adler32, unsigned long Adler, unsigned char pointer buff, and integer length. So it takes Adler, a buffer, and the length of the buffer. Opening up the function, we have unsigned long S1 equals Adler masked with 2 bytes that are all set to 1 in their binary. Unsigned long S2 is Adler bit shifted over 16 bits, masked with a bit mask of that would be 16 bits. Yeah. Yep, that makes sense. Int n for n equals 0, n is less than length, so we're going to go inclusively through 0 to length -1. S1 equals S1 plus buffer n, and then we're modulo base. S2 equals S2 plus S1 modulo base. And then we're going to return S2 bit shifted over 16 bits plus S1. Return the Adler of bytes buff 0 len -1. And I think that's it. Okay, end of page 10, on to page 11. Okay, so there's a little bit here. How is that connected? So there's a return. Okay, so this comment return the Adler of the bytes buff 0 len -1. That is the comment for whatever is coming next here. Okay, so this is a function right here. Unsigned long Adler32, unsigned char, pointer, buff, integer length. So you're going to take the buffer and the length of the buffer, and then you're going to return update Adler32, with 1L, so a 1 long, and then the buffer, and then the length. So update Adler is update Adler recursive then, because that is kind of what it looks like, because you're kind of setting the seed value to 1L, to 1, and then it looks like you're doing something recursive. So let's look for where update Adler is being called again. Update Adler 32. Update Adler 32. Okay, so it's not recursive. I mean, you probably could do something recursive, but it is iterative. So, because we're seeing update Adler being called over and over on an accumulator value right here. Okay, so now that we kind of get that, let's scroll back down. And let's see, that's all, this is all that is on page 11, and we're pretty much at the end of the document, it looks like. Let me scroll here for you. Yeah, that is the end of the document. So there you go.